if you pointed your boat straight across the river? How fast does the frog see you moving, and how fast does the observer on the shore see you moving? That's the real question. And to answer it, what we're going to do is we're going to do our vector addition again. I put the boat vector, I'm pointing it straight across, it's at 4 meters per second, but the current is 3 meters per second that direction. So to put that on, I'm going to put the tail of one at the tip of the other. And now I'm going to drop from the open tail to the open tip. And if you've been playing along, what you're going to realize is that this vector is now 5 meters per second. But the thing is that it's not going straight across, even though the boat's pushed straight across. And so what you end up with is this scenario where the boat is here, and even though it's trying to drive straight, it's being pulled down, so it angles this way the whole time. Which is weird to see the boat oriented this way, but going this way. And of course, one of the real questions is, at what angle? Right, at what angle? And this is a 3, 4, 5 triangle, and so we can call this angle theta. Theta, well, we say the tangent of theta, because I use opposite adjacent, is equal to the ratio of the opposite to the adjacent. So 36.9 relative to straight across. And that is what this guy on the shore sees. But what does the frog see? What does the frog along the river see? Well, every time your boat moves forward and gets dragged down, the actual frog goes down the river also. Again, he doesn't know he's moving, so you can just ignore this. And so what the frog sees is you just moving straight across the river relative to him at 4 meters per second. Which is pretty cool. Now, here comes the hard question. Because right now, if you leave here at A, B is straight across, are you going to land at B? No, because your boat's going like this. You're going to land all the way down here at C. But I don't want to land at C. I want to land at B. So what would I have to do to my boat? Which way would I have to point my boat so I can still land at B if I left A? That's the question. Because the river's going to drag us down, in order for us to get across, I would have to actually angle my boat upstream. True? I'd have to angle my boat upstream. Now, I know you want to apply some symmetry here. Right? We know we have to angle it here, but it's not 36.9 degrees, and it's not 53.1 degrees. What we have to do is we have to kind of see what the real situation is. The first question is, what is the speed of your boat? Right? The speed of your boat is 4 meters per second. So when I draw that in, I'm going to draw upriver. Because I want to go straight across, so I want to angle it upstream so that the river can pull me downstream. But again, it's a vector addition problem, so I'm going to add my two arrows together. Take the tail of one, put it at the tip of the other. And now draw from the open tail to the open tip. And this is not a 3, 4, 5 triangle, because what do you notice here? The 4 is the hypotenuse. So this isn't going to work. We're going to have to use a little math. Hold on. So when I go to solve for my resultant speed here, I know that that's dr for resultant velocity. So this is 16, 9 plus dr squared. 16 minus 9, how about 7? Square root of 7. So it's only going about 2.65 meters per second in the across the river direction. Which to me is pretty interesting. And then if I want to find this angle, and this is the thing that I want to know is, what angle would you have to launch it? That's the thing I need to know for sure. So I'll call that theta. So this time, because I know the opposite side in the hypotenuse, this time it's a little different. The sine of the angle is equal to 3/4. So that's the angle you would have to point the boat in order to get across the river. It turns out that these actually manifest in the real world, because let's say you wanted to fly, I don't know, you wanted to fly from Cincinnati to Detroit, okay? Cincinnati is down here. And Detroit is almost exactly due north of Cincinnati. The problem is that you could point your airplane straight forward. You can point your airplane north, due north, but the winds are which way? In general, the winds in our part of the country are out of the west. This is a thing in weather terms. They say a west wind is a wind out of the west, not a wind pointing toward the west, which is a little confusing. So in essence, instead of pointing your airplane straight across, you'd actually have to point it, that way. So your plane would be angled this way, but could go straight across. But in the end, to get to the actual relative velocity, the resultant velocity, it's only about vector addition.